Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 85 in our incredible new tutorial series where you are learning how to think like an engineer using the Arduino Uno R4 Wi-Fi. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee, poured over ice, no sugar, no sweeteners, none needed. And while you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Sunfounder Elite Explorer Kit. Now, hopefully most of you guys already have your gear, but if you don't, take a look down in the description. There is a link over to Amazon, and you can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot simpler if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And what I'm going to teach you is I'm going to show you how you can greatly improve the performance of your MPU6050 IMU project by incorporating a complementary filter. All right, so today's lesson, complementary filter. But I'm going to take just a few minutes and review how we got here. Started 5 or 6 lessons ago, and what I did was I showed you how to connect up the MPU6050. I showed you how to read the acceleration data from the 3 accelerometers and use that acceleration data to calculate the pitch and the roll of the IMU on your breadboard. All right. Now, what did we love about that? What did we love about the accelerometers? They are very fast. They make their measurements and report their results very, very fast. We love that. There is no drift. They are very, very stable over time in their readings. There is no drift. We love that. But what did we not love about the accelerometers? The accelerometers were susceptible to vibrational noise. Any vibration would lead to a high frequency error signal on your calculation of roll and pitch. So they were fast, there was no drift, but there was a noise problem. So then in the next lesson, I showed you how to implement a low pass filter. And what a low pass filter does is it filters out that high frequency data and it passes on through the correct low frequency signal. What was great about that? It was very accurate because you eliminated the high frequency noise and you had no long-term drift. So no drift, no noise. But what did we not love? When we incorporated that filter, the response of the accelerometer became just a little bit sluggish and it was going a little bit too slow. What did we do next? We turned on the gyros. And what I showed you is using the gyros, you can use the gyros by themselves to calculate the pitch and the roll of the IMU. What did we love about the gyros? They were fast. What else did we love? There is no vibrational noise. They are not subject to errors due to vibration. We love that. What did we not love about the gyros? We didn't love that there is a long-term drift. They're great in the short term, but if you leave them running overnight, they're going to be crazy, crazy, crazy out of whack because of the drift error. So if you look, what is it that we really want? What we really want is something that is fast, something that has no noise, and something that has no long-term drift. Well, with the accelerometers, a low-pass filter, the gyros, we could get any 2 of those 3 that we wanted, but you could not get 3 at the same time. So what I'm going to show you today is by incorporating a complementary filter into the project, we should be able to get something that is fast, no noise, and no long-term drift. Okay, sound good? I hope it does. Done a lot of talking here. Let me get out of your way. Let's come over, and I need you guys to come over to the most excellent www.toptechboy.com. You're going to want to use this happy little search tool, and you're going to want to search on something like reducing gyro drift in MPU6050 IMU. And then what you're going to do is you see this is our schematic. This is the GY87 module in your Sunfounder kit. On there is the MPU6050 chip, and it's very easy to hook up. You just take VCC to 5 volts, ground to ground, SCL to SCL, and SDA to SDA. Now, in showing you a complementary filter, I don't want to start from scratch. I want to start from where we left off last week, and then we'll kind of take that, and then we're going to add to that. We're going to add to that the complementary filter. All right, so I'm going to come here and you're going to copy that, and then you're going to come over here and you're going to paste it. And now we're going to run this thing just to make sure that the world is in proper working order, and then we can copy and paste, okay? It looks like it's going pretty well there. We are going to pop open our serial plotter. And let me get it moved over here where you can see it. Okay, hopefully this thing will come to life here in a minute. What it's doing right now, it's doing the calibration, and there it is. It comes to life, and then let's see there. I've got a roll, and I've got a pitch, and I'm getting roll and pitch just fine. I should put this where you can see that, right? So it's getting a roll, and it's getting a pitch, and everybody is happy there. Now you can see we're already starting to get a drift in here. We're already starting to get a little bit of drift, but that's one of the things that we're going to be taking care of today. Okay, so let's get rid of that. And now let's come in and see if we can begin to do what it is that we want to do. Now, what I want to do is I want to sort of step you through the different ways of measuring roll and pitch. And one thing we really like here, we really like roll raw and pitch raw. What is roll raw and pitch raw? That is just the calculation of roll and pitch that is coming from the accelerometers. Now on this pitch and this roll, that is the roll and pitch from the accelerometers with a low pass filter, added. And I don't want to just keep calling this pitch and roll because it's like we got so many pitches and rolls. Which pitch and roll are you talking about? So this is going to be pitch low pass LP, and this is going to be roll low pass LP, and then that would mean this would need to be LP, and this would need to be LP, like that. And then what we need to do is we need to come up here and we say, okay, there is a, where did we do that? Roll and pitch. Somewhere we had to define roll and pitch. Somewhere. Okay, roll LP and pitch LP, and then there's roll raw, pitch raw. Okay, so that is pretty good. Now let's come down here and let's just go ahead and kind of do this methodically, one step at a time. And so what we're going to come in here is we're now going to say that what do I have? I have my, I don't want to plot just the data from the gyro, just the rotational velocity. So I'm just going to say that this is roll raw. And so that is the roll value from the accelerometer. And I'm going to say roll raw. And that is the, again, from the accelerometer. And then here, what we're going to say is this is roll LP for low pass filter and roll LP for low pass filter. Now what we also have up here, we also have the roll from the gyro and the pitch from the gyro. We have the roll and the pitch from the gyro. So let's go ahead and let's do the roll from the gyro and the roll from the gyro. Like that. Okay, now why am I not doing pitch? Because I can't do roll and pitch. If I have 5 different ways of doing roll and 5 different ways of doing pitch, I can't plot that many out. So I'm going to start as we work through here just doing the roll, and then we'll come back later and we'll plot the pitch. As we go along, we'll be calculating pitch, but we're just going to be looking at the roll. So let's see where we are here. Let me download this, and I'm just sort of seeing if we're getting all the numbers that we think we should. None of this is new. This is just turning on things that we've done in the past and kind of getting them organized. Okay, there we go. Let's see here. Where is that? Okay, let me close that and try to open it again. Okay, there it is. So now what I want to look at is I want to look at roll raw, roll low pass filter, and roll from the G. And I'm going to turn these other things off, okay? So let's see what's happening. Okay, there is roll, but whoa, wait a minute. Wait a minute, what's happening? The red is roll raw, that's good, and the blue is roll raw, and the red is roll low pass filter, but the roll gyro is going the wrong way. Now, why is that? We weren't really very deliberate in defining what direction is this roll positive or is this roll positive? And it looks like it was one way for the accelerometer calculations, and it was the other way for the gyro calculation. Well, if we're going to fuse those two together, we have to make them match. And remember, it is the Y gyro data that we use in order to calculate the roll from the gyro right here. This roll gyro is from GY. And so if we want it to match the accelerometer, we're just going to change the sign of this whole thing, including the offset. Okay, so now also, yeah, let's just do that. Let's do that and see what happens. So here we hope that it's all going to go the same way. Okay, that's looking good. All right, here we go. Let's give it a second. And while I'm thinking, I'm tired of waiting 1,000 points. 1,000 points here. I'm just going to do 100. So in the future, the next time we run it, it's going to run, it's going to run quicker next time. Okay, so that is running now. And so now if I do a roll, I've got all 3 rolls. Okay, now what do we see? We see that the roll gyro is very fast. The green is very fast and there's no noise. But if we just leave it there over time, that roll G is going to drift off. Now, if I look at roll raw, that's the blue. What do you see? You see that it gets vibrational problems. So like as I'm shaking it, you see the noise in the blue? The noise in the blue. Now, what do we like about the red, the roll with the low pass filter? We like that there is no data and there is no noise in that. So if you look at the red signal, there's no noise there. Now I'm going to turn off the gyro, and now we're just going to look at the raw accelerometer roll and the low pass filtered roll. And that is great. We don't have any noise in that red signal, but what? You see it's slow? It's a little bit sluggish, okay? To where if we look at the roll G versus the roll from the accelerometer with the low pass filter, you see that roll G is fast and no noise. But what we know is after a while, look there, it took off, it's off to the races. Okay, so you can never really completely trust the gyros. Okay, so what do we want to do? We want to come in and we want to create something that is going to be the best of both worlds. Okay, so what I'm going to do is I'm looking and thinking what new variables that I need to create. And I think what I'm going to need to do is I'm going to need to just come down here and let's start by just talking about how we are going to do this. Okay, how we're going to do this. And so I'm going to come down after I've done my other calculation of the low pass filter, and I'm going to come up with a roll with the complementary filter and a pitch with the complementary filter. And you know what? If we are going to use those, we better declare them up at the top. So we're going to come up here and we've got pitch and roll. That's kind of awkward, isn't it? Let's do it like this. Okay, so I've got roll and pitch, I've got roll and pitch, and then I'm going to say I've got this new float, I've got roll with the complementary filter, and I'm going to set that to 0 just in case we do any summing on it, and float pitch compensation, or comp. Let's just say comp. And that's equal to 0, like that. And let's make sure that we did that, just called it comp down here. Yeah, roll comp and pitch comp. All right. Now, what we would really, really love to be able to do is we would really love to be able to come in and say, give me a 0.1 times the give me a 0.1 times the roll raw, which is from the accelerometer, right? And then give me a 0.9 times the roll gyro, okay? And those then would add up to the compensated value, and I would sort of have a very nice long-term signal coming from the accelerometer, and the fast short-term signal would be coming from the gyro. And you see, you kind of think about fusing them together that way. But let me show you what the problem if we did it that way. The problem is if we look at this calculation of the roll from the gyro, we have this term that we're adding each time. And that term is not perfect. That term has a little bit of error, and it is added to roll G. The next time through, we have another little bit of error that is added to roll G and the old error. And so you see the way this roll G is equal to roll G plus millis, it is accumulating the error. Each time through, the new value has all the old error plus the new error, and over time it's just going to drift off into outer space. So the problem with this is that if we now take this roll G that has an accumulating error and we just add it here, it is adding to the roll complementary filter an accumulating error, and basically this is just not going to work at all. Okay, so this is how we are going to do this. We're going to take, let's say I'm going to take 25%. I'm going to take 25% from the accelerometer, from the accelerometer, roll raw, that's unfiltered. This is the filtered one here, but I'm just going to take the unfiltered one. And if that's 0.25, this should be 0.75. And what am I going to take? I am not going to take roll G. I'm going to take roll comp. Now, at this point, you cry foul and say, whoa, all you did was just create another low-pass filter. And you got the same problem as you had with the one above. Yes, but I'm going to do something else. I'm going to add to the roll comp. I'm going to add a term that depends on the gyro. And I'm going to call that delta roll. Now, if I just added in here roll G, like that, the problem is, again, roll G has the error, and then I'm just going to be adding that integrated error, and it's all going to end up here, and this is going to drift. So instead of adding the roll from the gyro, I'm going to add the delta roll, which means the last time through the loop, how much more angle, what is the increment in angle that the gyro saw. Okay, and then same thing with pitch comp. I'm going to say 0.25 times pitch raw plus 0.75 times pitch comp, and I better put an uppercase C there, is not counted as an error if you catch it before you run it. And then what here? The change delta pitch, like that. Okay. Now, if I'm going to use these new terms, delta roll and delta pitch, I better define them. I better declare them up here. And where were we doing that? Roll G, pitch G, yaw G. It's kind of awkward. I did it in two different places. Okay, we'll do it here. So we're going to say, what did we call that? Delta roll. We're going to say that's 0. And then delta pitch, and we're going to call that 0, like that. So delta roll, delta pitch, and those are going to be what? Floats. Floats. Okay, does that make sense? Delta roll, delta pitch will come back down here. Okay, and so we're going to have delta roll, delta pitch. Well, if I'm going to use these, I've declared them, but I'm going to have to define them somewhere. Well, we're going to come back up here where we're doing our gyro calculations. All right, now the actual roll, what angle you're at, is the angle you were last time through plus the increment. And this, my friend, is the increment, right? It's what was the elapsed time multiplied by the rotational velocity. So what I'm going to do here is I'm going to come in and I'm going to just say delta roll is going to be equal to what? This term. Okay, and then delta pitch is going to be equal to that same term, only that does not come from x, that does not come from y, it comes from x, like that. And let's make sure you saw everything that I was doing there. Okay, so what I did was I just got this whole term, that's the delta, and I pasted it here. All right, and then I pasted it again here, and when I pasted it again here, what did I do? I just changed that to GX. So now I have a roll from the gyro, that's great. I have a pitch from the gyro, that's great. And then I have how much did the roll from the gyro and the pitch from the gyro change the last time through the loop, and that is those two. And then it is those two numbers that I am adding into this complementary filter. So my long-term data is going to come from where? From the accelerometer, the raw accelerometer. But my short-term quick change data is going to come from what? From this term by using this, incorporating this term delta roll, okay, on top of the other one. So you see how you're kind of blending the data together, and this is actually called sensor fusion, okay? So now, let's come in. What do we want to print now? What I want to print is roll raw, roll LP for the low-pass filter, roll G, just the raw data from the raw roll from the gyro, and then this one, what we are going to do is roll complementary, and then roll complementary, like that. And then these other two, we are just going to turn those off for now. We need that comma. Okay, do you see what I'm commenting out? Because I don't want that other stuff messing things up, confusing things. So we'll come and say edit, and we will say comment, like that. And now I think we're ready to run this. So let's see what happens, okay? Does it make sense, the magic that you just saw happen? Delta pitch. Why did it not like delta pitch? Delta roll, delta pitch. Did I write those backwards up here? Delta roll, delta pitch, delta roll. I must have misspelled something. Oh, no, I know what I did. Where was that? Delta roll needs the semicolon, and delta pitch needs the semicolon. Okay? Let's run this thing. All right, it's going. I always turn this back on and then I forget to turn it off, and sometimes I block a line of code, and I know how you guys do not like that. Okay, Let me move this over here. All right. Now what we're doing is we're starting at 0. That's good. Let's see if it's alive. Okay, and they're all 3 moving. Okay, now we love that. We love that. Okay, we love that. Now let's go in and let's look at these things. So let's look at the roll compensated versus the roll raw. So this is the compensated filter, the complementary filter that we just did compared to just the number coming from the accelerometer. And what I want you to see is, do you see that purple is really keeping up? That purple is keeping up very well. But what do I not like? I'm seeing more. No, okay. What I want you to see is now when I tap this, that noise is only going to the blue, the accelerometer. I'm not getting noise in the orange. Okay, so what I want you to see is, wow, look at that. Okay, look at that. So I'm tracking very, very quickly. I'm tracking very, very quickly as fast as I am on the accelerometer. Now to show you this, let's look at the accelerometer with the low pass filter. Okay, let's look at the accelerometer with the low pass filter. Let me move this over so you've got a little bit better view of it. Okay, so I'm looking at the low pass filter compared with the complementary filter. Okay, look at that. So do you see, I wish it was a different color, but that complementary filter, the orange, is really going faster than the red. The orange is going faster than the red, and we do love that. The orange is going faster than the red. Now let's look at vibration. And you see neither one of these really has a vibration signal. Neither one of them is having a vibration signal. And so that is really good. Now let's compare our complementary filter to our complementary filter to just the unfiltered roll that we're getting from the gyro. And you can see that we are really just as fast. We are really just as fast with the orange as we are with the green. Do you see that? But what do you notice? You notice that the green, the number coming from the gyro, the calculation is already starting to have a little bit of drift in it. Now, just for fun, what I want to try here. So, man, this is really exciting. What if I deliberately add an error to the gyro? How does this new filter handle a really bad case of drift in the gyro? So I'm going to come here on that roll, and I'm going to add a 0.1, which is just deliberately forcing a noise signal on that y-axis gyro. And let's see what that does to our complementary filter. So does our complementary filter work with a really badly drifting gyro? Okay, what is happening? The green is off to the races because that is the error that I just put in on the just calculation from the gyro here, the roll G. But now what I want you to see is the complementary filter is still working. And the complementary filter one, the one with the complementary filter is not drifting. Okay, it is not drifting. What else? There's no vibration, right? There's no vibration. So boom, do you see the power of the complementary filter? What do we see here? We are as fast as the accelerometer. We are as fast as the just raw gyro, but we don't have any noise and we don't have any long-term drift. Even when we deliberately add that huge drift component, it's not making it down through our complementary filter. So that is pretty exciting. Now, I'm trying to think what else we should do there. What you can do is, now you see when I did that, just to be fair, I set both of these to like 0.25 on the accelerometer and 0.75 on the, on the integrated values. So it's a fair comparison between those two. But what you would really want to do now is you would want to go in and you would want to play with these a little bit. Like I wonder what would happen if I took this to 0.1, 0.1, and then I took this to 0.9. 0.9. What's going to happen there? Let's see what's going to happen there. Is it going to still be fast enough? I'm trying to, I want it to stay fast, but I want to maybe filter out a little bit more of that accelerometer data, a little bit more of that vibration. So let's see what happened when we did that. And I'm going to take that silly error out that I just put in, because that is going to get annoying after a while. So now let's try this. All right, then here we go. We get that, and there it goes. Okay, so now okay, do you see how that green is still the, what am I looking at? That's the gyro. So what we're going to do is we're going to look at the raw versus the compensated, okay, like that. And do you see that that orange, that compensated, is still very fast? But as I move, I'm getting less of that. I'm getting less of that ringing in this one by putting a little bit more trust in the gyro, and it's still very, very fast. You see the blue is getting some ringing when I move it very quickly, but then decompensated is dead accurate. It is dead accurate. Okay. I think the last thing that I want to do here is I want to make sure that my pitch is working as well. And so what I'm going to do now is I'm not going to do roll raw. What I'm going to do is I'm going to do the roll compensated. So what I'm going to do is roll comp. And I keep saying compensated. It's complementary. Roll complementary. Roll complementary. And then I am going to do what? I'm going to do pitch complementary and pitch complementary. I want to make sure that my final answer is working. And then remember how we were calculating yaw, and what did we call that? Just yaw G, yaw from the gyro. Okay, yaw from the gyro and yaw from the gyro. And then I got to leave that comma, and then I don't want these. I'm going to comment those out like that. And so now I've just got roll, pitch, and yaw. Now, why did I not do any filtering on the yaw? The problem with yaw is if you look at this, the accelerometers do not see, the gravity vector does not see rotation this way. So the yaw, the accelerometers cannot see yaw. Only the gyro sees yaw. So I can't right now stabilize that yaw number any more than it already is, because the accelerometers are absolutely no help on that one. Okay. So let's see what happens now. And let me see if I can line this up. I'm going to try to line it up with the graph paper so that we can kind of check the yaw. Okay, so now we're going to pop open that serial plotter. We're going to move it over here where you can see it. Okay, and so I've got roll compensated or complementary, pitch complementary filter, and I've got the yaw. Okay, and so now let's start by just checking how well we are on yaw. So I'm going to go to the perpendicular lines there. And when I go to the perpendicular lines, what I'm seeing is right almost precisely at 90. Okay, I'm seeing almost precisely at 90, or I can go back to 0, or I can go to 90 like that. Okay, come back here to 0. I disturbed it. Okay, so yep, that is working. yaw is working. And somehow, as I'm yawing, I'm messing with the wires and making it unhappy. You know, we need to kind of lock those wires down a lot better. So now what we have is the roll is working. You see how fast that is? Fast, and there's no noise. Okay, that's fast and there's no noise. Now let's try our pitch. Okay, whoa, look at that. Pitch, let's see. Yep, down to 90. Pitch. You think pitch is fast? I think pitch is very fast. The pitch is working really, really nice. The roll is working very nice. And so, boom, we have got this thing working. So now at this point, this is almost as good as we can do, because we're using the 3 accelerometers, we're using the 3 gyros, we're fusing the data together. Where are we? We are very fast. We don't have any vibrational noise, and we don't have any long-term drift. So we're going to call this a success. But now, why do I say almost? Why do I say almost? Did you see as I was dropping this thing and playing around with it, what did I do? I kind of confused the yaw a little bit. And so when I come in here and I set this to where it was a while ago, it's no longer reading 0. It looks like I might have like a, maybe an 8 or 9 degree error in there. And why is that? Because I can't compensate the yaw with the accelerometer. So what we need is we're going to need to incorporate a new sensor to try to help us do better on yaw. Now, what have we done so far? We've done the pressure sensor. We've done 3 accelerometers, XYZ. We've done 3 gyros, XYZ. That is a total of 7 sensors. This module has 10 sensors. The other 3 sensors are magnetometers, looking at the strength of the Earth's magnetic field in the X direction, in the Y direction, and in the Z direction. Okay, so it has magnetometers. So what we're going to do is next week we're going to try to turn on those magnetometers, and that's how a compass works. A compass has a magnet. So we're going to try to lock in that yaw value using a magnet. Okay. All right, guys, I hope you're having as much fun with this as I am. I just think it's so cool to see the progress that we've made, not by spending more money on the sensor, but by using math that allows us to get more performance out of the low-cost sensor that we have. So that is a lot of fun. It's at this point that I always give a great big shout out to you guys who are standing with me on Patreon. Without your support, I would not be able to continue to produce fresh, in-depth, quality content every single week. And so thank you guys. You can also help me by giving me a thumbs up on this video and leaving a comment down below. That will help with the old YouTube juice. If you haven't already, subscribe to the channel. When you do, make sure you ring that bell so you'll get notification when future lessons drop. And as always, most importantly, share this video with other people, because the world needs more people thinking like an engineer and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.